Hi everybody. I'm going to talk to you today about Leapfrog, Certified Equivalence for Protocol Parsers. This is joint work with Tobias Capet, John Serachino, Nate Foster, and Greg Morissette. And we're motivated in particular by network security. And people have observed that parsers have a fundamentally important role in security because before you decide what to do with a packet, you need to first parse it. And so if your parsers at two devices disagree on what a packet is, if this middle switch thinks the packet is perfectly innocuous, and it's maybe something else in reality, you have a problem. And so we're interested in solving this with equivalence checking for parsers. And this is a problem for networks, but it's a bigger problem nowadays because programmable networks are becoming more and more common. And in a programmable network, a programmer writes the parser. It's not designed once by a hardware engineer and validated on millions of standards compliant test packets. So it probably has bugs in it. And it's probably written in a language like P4, which is used to program these programmable targets. And for P4, the situation is something like this. Because P4 is a high-level language, or a reasonably high-level language, it's not actually what's going to happen on the hardware device. You're going to optimize your parser heavily to meet throughput requirements of modern networks, and you're also going to have to move things around to meet the strange resource constraints of your hardware accelerator or your other target. So if you want to know that all your parsers are speaking the same language in a very literal sense, you probably want to know this. And I would say the best way to prove it is to translation validate your parser compiler and prove your source parser's equivalent, right? Something like that. So maybe I can show you some parsers and be very explicit about what this kind of optimization looks like and what kind of bugs I'm thinking about. So P4 parsers are written as state machines. In the code that the programmer writes, there are states, and there's code in each state. And it looks something like this. So this parser is parsing MPLS, which is a tunneling protocol. There's a sequence of MPLS headers. And then it's parsing UDP protocol, which is a datagram protocol that's standard. And the way it works is you start in the start state with your packet, and you have this store of variables you're going to populate with data from the packet. So this will first read 32 bits from the MPLS header into the MPLS variable, and then it will branch on the bottom of stack bit, which is the 24th bit. For this first one, it's 0, so it'll keep parsing, and it'll keep parsing until it sees a 1. So the second one is a 1, and you transition to the next state. And then you read your UDP header, and you accept the packet. This green state is the accepting state of this state machine. Okay? And if a programmer wrote something like this and compiled it for some kind of hardware P4 switch, it's probably going to look more like that on the right. It's going to be maybe loop unrolled, maybe vectorized, maybe it's having to create new states to accommodate some resource constraint that exists. And it's not immediately obvious to me that these two things are the same, that they're recognizing the same collection of packets and doing the same thing. And it's maybe not immediately obvious to you either. And it is late on a Friday afternoon, so I won't make you figure it out. Fortunately, we built a tool, Leapfrog, that can prove these two things equivalent and even give you a Cox certificate that they're equivalent in terms of the semantics of these automata. So you won't have to read a long trace of SAT queries and think really hard about it. There's a proof certificate at the end that you can just check. What Leapfrog consists of is a model of these P4 automata, which is a simplified model of P4 parsers, an algorithm for checking their equivalence based on classical ideas from automata theory, and an implementation in Coq. Today I'm going to talk mostly about the automata and algorithm, and I'm going to avoid throwing too much Greek at you, but I just want to give you a sense of where the problems were and where we had to put make choices about optimizations to make this sort of more efficient. And I'm happy to talk offline more about the Coq stuff. There's a bit at the end, but okay. So I showed you some P4 automata, so you maybe have an idea of how these things work, but I just want to tell you, there's states. Each state has some code in it, which is a sequence of extract statements or assignments to variables. And then there are special states, accept and reject, which is how you mark that you're done parsing the packet. I usually won't draw the reject state. Now, in each state that actually has code in it, there's an operation and some transitions, and the operation can update the variables, and then the transition can branch on their contents. And this is not how a normal state machine is set up, right? These are not deterministic finite automata where each edge is labeled with a character from some alphabet. There's something funny going on. But fortunately, we can give them semantics as finite automata and then sort of bring to bear the tools of automata theory and stop thinking about P4 so much, I would hope. But so what we need to define is a set of configurations, set of final configurations, and a transition function. I'll give you these each in turn. So the configurations are just triples of a state, a store, and a buffer. And the buffer is always going to be smaller than the amount of bits you would like to read in order to run your state. So if your operation reads 64 bits, your buffer won't be any longer than 64 bits. And the final configurations are the ones where you're in the accept state. Okay, this is very straightforward, I hope. And then there's transitions for these things. So if you're already in a terminal state, if you read another bit, and I'm just going to give the rules for one, if you read another bit, you're going to reject the packet because you already made a decision. If you're in a state that actually has code in it, then you probably want to run the code. But if your buffer isn't full, you can't. So if reading the next bit won't give you enough to run your full operation, all you do is buffer the bit. Okay, so there are a bunch of these buffering transitions where you're just taking the one you read or the zero, as the case may be, and appending it to the buffer and not changing anything else. And once your buffer is full, then you actually have some work to do. So given this condition, you define a new state, or a new store rather, as prime by running your operation with your full buffer and your current store. And then you branch on it using your transition to get out a new state, q prime. And you clear the buffer since you're now in a new state. Okay, so these are the transitions. And the point here is that most of them are going to be buffering transitions. Okay, but this is an automaton. It's a standard automaton, and so you can bring to bear the tools of automata theory. So there's a natural notion of language equivalence based on the languages recognized by each parser, and there are textbook decision procedures which you can throw at these things. They're not going to scale to P4A, but because our symbolic algorithm is based on them, I will show it to you anyway. The idea is to compute what is called a bisimulation, right? So you want a relation between the state spaces of your two automata, which is closed under steps, and only relates final or accepting states to other final or accepting states. And this means that if R relates to states, then they have to be language equivalent by basically an inductive argument. And now the problem of proving language equivalence comes down to computing one of these relations. Okay, so a concrete algorithm for doing this, which is based on Moore's algorithm, Moore's partition refinement algorithm, is you start with all the bad states. You actually try to compute by simulation by over-approximating it and removing things. So the little skulls in the corner here are the pairs of states where one automaton has accepted the packet, but the other hasn't. So if you're in some pair of states like that, you know you have a problem. These parsers are not equivalent. And then what you do is you work backwards using the transition function through these concrete configurations until you saturate your relation. And the fact that this terminates is a theorem in automata theory. It has to do with the state space being finite. But once you've done that, once you've closed this thing under backwards steps, then you can just check if your start state is outside of the bad states. All the pink stuff is non-equivalent configurations, and the remainder is a bisimulation. Okay. This is not working. This doesn't work. This won't work for me. So the problem is that the configuration space is, of course, enormous. These are big bit vectors, and most of those bits don't matter at all. So there are, on paper, 2 to 128-ish configuration pairs for that example I showed you earlier. And if you run the concrete algorithm on that, you'll probably have to wait until the heat death of the universe to see that they're the same. The problem is, yeah, you have a concrete set of these pairs, so that's not going to be workable. And you're also searching that space one step at a time, where most of these transitions are these buffering transitions that are sort of a bureaucratic definition and not really essential to how the automata are behaving. So we fix this with 2 optimizations. One, unsurprisingly, is to use a symbolic representation for this enormous state space. And I refer you to the paper for the details. I won't show you any Greek today, as I said. So rather than have a concrete set of states you start with, you have a formula that describes a region of the state space that's undesirable. And then you close that under backward transitions with a weakest precondition operator. Instead of taking steps backwards, you're doing some sort of symbolic operation to move backwards through the state space. And this lets you close it, again, under transitions. And then you check that a formula referring to your start states is not contained in the thing you built up. So here, there's new machinery. There's a weakest precondition transformer, and you also need a decision procedure for checking, containment in order to know that you're done, and also to know that your start states are outside of the bad states. Okay, but this is still running one bit at a time. So the weakest precondition operator has this unfortunate behavior I will show you here. This formula means I'm in the accept state on the left with nothing in the buffer of length 0, and similarly on the right, okay? And if I run the weakest precondition transformer on this, I end up in this configuration. I have a 63-bit buffer and a 223-bit buffer. And if I run it again, I'm in this state. And if I run it again, I'm in this state. And it goes on. But eventually you get to a state where something's actually about to happen. You're actually going to run some code, which is the hard part of program analysis. But you have to do all this work in the middle, and in the presence of more complicated control flow, this affects the asymptotic complexity of the algorithm. So we introduced leaps, the kind of namesake of this project, to jump over these bureaucratic transitions. And then you can do it in 2 steps, something like this. And we came up with this basically by running the 1-bit algorithm and being shocked by how slow it was. But it turns out that this is an instance of what is called bisimulation up to closure, or bisimulation up to a closure. So it was actually already a concept in automata theory we could use to prove the technique sound, which was quite nice. Yeah, that's all I have to say about theory. So that's the algorithm. There are more optimizations than this that we needed to do. You can see the paper for full details. 5 minutes? OK, thank you. The implementation is in Coq. There's a full mechanization of what I just showed you. And the algorithm is defined as an inductive relation. So it sort of encodes a semi-decision procedure. If you'd like to hear about semi-decision procedures, stick around for Leo's talk. Don't ask me about that. We use a plugin called MirrorSolve that we built to interact with a SAT solver and avoid having to do these symbolic computations and decide them in Coq with Coq code. And we did a feasibility study on a collection of sort of representative examples of parser optimizations and changes. Yes, OK, so I won't tell you about all the examples, but one I'm particularly proud of was ParserGen. So this is actually an early paper. It predates P4, in which Glenn Gibb and others described how to optimize programmable parsers. So they had a format for describing a collection of parser headers, and they would compile it down to these kind of low-level match action tables, which are sort of what the hardware offers to implement these things. We built a translation from these low-level representations of state machines up to P4A, and then we handed them to Leapfrog, and we were actually able to translation validate the results of this tool and get out Coq certificates of equivalence for all of them. So that was very exciting. OK, thank you for your attention. Thank you. And thank you to my collaborators. I'm happy to take any questions.
Thank you. OK, very cool. We have time for a few. OK, then I'll start. So my question was, your algorithm seems to be exploring the space backwards to basically prove by simulation. So that seems like it would mean that you won't find a counterexample in case the by simulation cannot be established. Is that true? Because you might just end up in, for example, some pair with some pair of states that are actually not reachable, for example, right?
Yes. Okay.
So in other words, if you want to actually identify a bug, okay, where 2 protocols disagree on something, then you would probably not be able to do it with your technique.
So yeah, okay. So one answer to your question is, which is not exactly what you're asking, is there's another optimization here that I didn't show that's basically a coarse reachability analysis. So it's avoiding a lot of ridiculous states that are on the face of it unreachable. But if the algorithm fails, what you get is basically a big verification condition that didn't go through. But I would suspect, so at the end, you're checking basically that your start states are not contained in this big thing you computed. And if they are in it, then you have a problem. That's what you're describing. And I would think you would be able to extract some kind of witness from that, but I haven't thought about this problem too much.
Yeah, might be interesting, right? Because you might want to identify problems that you encounter, not just.
It would be nice to have like a witness, a string.
Exactly. Okay. We do have time for one more. I don't see any question on Slack, so it's our time.
I'm actually curious about the mix of technologies. So you use SMT for reasoning with a plugin to connect to Coq.
Yes.
How does that affect your SAN story? And what does SMT give you that Coq would not give you in this case?
So we have these large formulas we're deciding with the SAT solver. Right now, we're not doing proof reconstruction. So it's set up as a tactic. So, and we're keeping things in a, I think it's in EPR right now. So it's in principle possible to do proof reconstruction here, but we wrote the entire tactic. So it was kind of out of scope for this work, but you could in principle do proof reconstruction. I would like if the whole thing was a Coq decision procedure. I would like to hear about, how hard it is to do decision procedures for first order logic over bit vectors, basically, in Coq. But yeah, I think that performance-wise, there's a lot of problems here because of how we did it, like that it's producing a proof term, and we're running the whole thing essentially in LTAC. Like there's a lot of room for improvement there. So I would be happy to talk to you later. Thanks.
Okay, thank you, Ryan. Thank you very much.
Thanks, everybody.